In this lecture, we discuss how to create infinite impulse response filters. Unfortunately, the techniques we use to create finite impulse response filters cannot be used to create infinite impulse response filters. Since analog filters are typically created with feedback systems, much like IIR filters, the simplest method for creating IIR filters is to first design a prototype analog filter and then transform that filter into a digital filter. I will refer to the analog filter as our prototype filter and the digital filter as our desired filter. Mathematically, we can create our desired filter from the prototype filter if we know the Laplace transform of the prototype filter. Since the Laplace transform exists on the S-plane, we need to map all points on the S-plane to the Z-plane of digital filters. We compute this mapping with the bilinear transform. When we apply the bilinear transform, we find that points on the imaginary axis on the S-plane map to points on the unit circle on the Z-plane. We also see that points to the left of the imaginary axis on the S-plane map to points inside the unit circle on the Z-plane. The mapping also shows that points to the right of the imaginary axis on the S-plane map to points outside the unit circle on the Z-plane. The analog frequency response of the prototype filter can be found by plotting the function along the imaginary axis in the same way that we can plot the digital frequency response of the desired filter by tracing the function along the unit circle. This means that we have to evaluate the result of the bilinear transform at e to the j omega. Unfortunately, converting filters from the analog to the digital domain via the bilinear transform creates some artifacts. Since we are converting the filters without considering a sampling frequency, we must determine exactly how the analog frequencies that range from negative infinity to positive infinity map to digital frequencies that range from negative pi to pi. With some creative math, we can show that the digital frequency response of our desired filter equals the analog frequency response of our prototype filter evaluated at alpha times the tangent of omega over 2. This tangent function mapping is important because the tangent function mapping enables us to map an infinitely long analog frequency space onto a digital frequency space that is bounded by negative pi and pi. Notice how the tangent function asymptotically approaches pi as the analog frequencies go to infinity. This mapping means that our digital filter's frequency response will resemble a squished version of our analog filter's frequency response. For example, suppose that we had a prototype filter whose frequency response looked like this. The digital frequency response would have the same general shape, but the higher frequency steps would get progressively narrower. The alpha parameter allows us to tweak how severely the higher frequencies get squished. As alpha increases, the lower frequencies are squished more, while the higher frequencies are squished less. From this lecture, you should have learned how points on the S-plane map to the Z-plane, and how the bilinear transform warps the frequency response of prototype filters to create digital filters. It is critical that you remember that the bilinear transform does not take sampling frequency into account. These changes in assumption necessitate frequency warping to map analog frequencies to digital frequencies.